there. Thanks for stopping by. I didn't hear you. Hopefully by now you're comfortable with some of the compound interest material we've been looking at. You know, a big part of personal finance does involve vehicles and purchasing your dream vehicle the same way I have. So, let's going to give you a situation. Suppose Ben has $5,000 he's saved towards a vehicle he'd like to buy, and he's decided he's going to put that money away and let it collect interest for a year and buy his new vehicle in a year. Maybe that money collects interest at 2.5% compounded monthly. And that's somewhat of a realistic example, but we might wonder, how did Ben magically come up with $5,000? It's not very often you just all of a sudden have a lump sum of money. Maybe you inherited that money, that's a possibility. Maybe it came from a tax return, and we'll talk about taxes as well in this unit. That's a possibility. But more likely, Ben saved that money over time. Maybe he saved $50 or $100 every week or every month or whatever it might be. The idea of making savings over regular intervals like that, like $50 every paycheck or something, that's called an annuity. And that's the next part of the course we're going to look at. And we're going to learn that whether you're saving for a vehicle or whether you're borrowing money for a vehicle, in either case, that's what's called an annuity. And we're going to look at some of the math behind that. So come on, let's get to it. Oh, geez! Hey! Back here! So let's start with a simple problem about Ben and the $5,000 in his savings account that's going to collect interest at 2.5% compounded monthly. And we want to know exactly how much money Ben will have in 1 year for his new vehicle. So this is just like last week, just an example of using the compound interest formula, where our principal is $5,000. Our interest rate is 2.5%, but we have to divide that by 12 to get a monthly interest rate. It's compounded monthly. And in 1 year, that's exactly 12 months. So our end value is equal to 12. If you plug that in onto a calculator, you should get $5,126.44. So at the end of the year, Ben's $5,000 has turned into $5,126.44. because he's collected some interest, $126.44. Okay, let's move on to the new situation. In this situation, Ben still wants to purchase a new vehicle, and he still has a year to save for the new vehicle. But instead of having $5,000, at the end of every month, he's going to deposit $450 into a savings account that pays interest, again, at 2.5% compounded monthly. And the question is, how much will he have in his account after 12 months? Notice how different this is than the compound interest example. This is a series of payments, $450 every month. And that's an example of an annuity. So in this course, when we say the word annuity, we just mean a series of payments made at regular intervals. So that could be, like this example, Ben putting $450 into a savings account 12 different times over a period of 12 months. It might also apply to a loan as well. A loan is an example of an annuity. When you buy a car and borrow the money and you pay back the loan every month or every week, that's another example of an annuity. If you were to Google the word annuity, you probably hear a lot about insurance. That's not the definition we're using in this course. We're more broad with that definition. Any series of payments, we're going to call an annuity. Don't worry too much about this information here. A simple annuity is when the compounding period and payment period are equal. Don't worry too much about that yet. We'll talk a little bit about that later on. So let's revisit this problem with Ben. How do we figure out how much Ben will have after 12 months? I mean, one way to do it is $450 times 12, but that doesn't take into account the interest. And the interest is kind of complicated. Every month there's a different amount of money in his savings account, so a different amount of interest is collected. So one rather painful way to look at this problem would be to look at every single month on its own. So for the timeline of this, you need to realize that he's making these payments at the end of every month, and we want to know how much he has after 12 months. So technically the easiest one to figure out is the $450 he puts in at the end. That doesn't collect any interest because it doesn't have any time to collect interest. The $450 he puts in at the first month, that actually has 11 months to collect interest. And so that money, using the compound interest formula, okay, we'll just write here, will be worth 450, take your interest rate, divide it by 12, and like I said, 11 months to collect interest. That actually works out to $460.42. So that first $450 collects a little over $10 in interest. The next month, that interest only has, or that money only has 10 months to collect interest because it's in there for 10 months. The third month, that money only has 9 months to collect interest. And let's see what happens if we continue the pattern all the way down. And there you see I filled in the rest of it for you from 11 all the way down to the month 11 only has 1 month to collect interest, and then month 12, no months. Now notice that these amounts are going to go down every time, 460 to 459, because every time I go down a month, that's 1 month's less interest that $450 can collect. So the money that's in there for the longest collects the most interest. Now I don't imagine you care to write all that out, and I don't imagine you care to add it all up, but if you do, you will find you get $5,462.31 total. Now thankfully, this is not how we need to solve problems like this, because could you imagine if we changed the question so that Ben was saving for, instead of 1 year, like 3 years? All those calculations, we'd have to do 36 of them. There'd be 36 payments. There is a formula to solve this problem for us. And there it is. It's called the future value formula, or final value formula for an annuity. It's not a simple formula, but it is pretty helpful. Let's just walk through it together. FV is the future value of the annuity. So in this case, it's the answer, $5,462.31, the final value or the future value. R stands for regular payment. So Ben made regular payments of $450. I is the interest rate. Now it's the same as the compound interest formula. The interest rate is per compounding period. So you have to divide it by 12 if it's monthly, or divide by 2 if it's semi-annually, or divide by 365 if it's compounded daily. And N is the number of payments, kind of like time. So as an example, we could use this to figure out Ben's final value of his annuity. And let's do that. So the R value is 450. So I'm replacing R with 450. Okay. Bracket, bracket. The interest rate is 0.025, 2.5%, but I have to divide it by 12 because it's compounded monthly. Okay, my N value is the number of payments, which is the same in this example as the number of months, which is 12. And then finally, my interest rate goes down here as well. Now, what I always like to do is I like to put brackets on your brackets in, because on your calculator, you're probably going to need those brackets down here, because your calculator doesn't know when you hit the divided by button, you mean there's a big fraction here. And so it's important that you have that. Now, you can get your calculator out now if you like and try to type all that in. It is sometimes a bit challenging to figure out how to get that all onto your calculator. There's a couple ways you can do it. You can type it in basically exactly as seen, as long as you include these brackets. If you have a calculator that shows what you're typing in, it's a lot easier. I'll show you a calculator I have on my computer here. And let's just clear that up. And we will try to work through this together. I'm just going to start with the numerator. So 450 times bracket, bracket. Okay, so I've got those two brackets there. Square brackets and curved brackets or parentheses doesn't make a difference. They both mean the same thing. 1 plus 0.025 divided by 12, close the bracket. My power button is right here on this calculator. It's kind of a funny looking one. Y to the power of n to the power of 12. Take away 1, close bracket. That's the numerator of the formula, the top of the fraction. I might as well hit equals right now. Okay, I get 1137. Divided by, and here's a very important set of brackets, 0.025 divided by 12, close the brackets, hit equals, and we see we get the exact same answer as before, $5,462, and if you round to the nearest cent, that is 31 cents. So it might take a bit of practice for you to figure out how to do that in your calculator. That's part of today's lesson for sure. Here's a simpler example. In order to save for her own college education, Rachel's grandparents provided her with a gift of $1,000 on her birthday. Rachel invests that money at 2.1% compounded annually. How much will she have after 18 years? So instead of saying on her birthday, I should have said every birthday. That's what I meant here. Every birthday. So 18 times every year on her birthday, she gets $1,000 put into the savings account to help for her college education. So again, it's important to understand that this is an annuity because we're talking about 18 different payments, regular payments, not a one-time payment. So we're going to use the future value formula again. Can you see why this example is actually a little easier than the example involving the car? Why is that? Well, the answer is that it's compounded annually. So we don't need to change the interest rate. We just need $1,000 for our regular payments. Our interest rate is 2.1% to the power of 18 years minus 1 all over 0.021. So this is a bit of a simpler example. If you type all that into your calculator, you should find that you get $21,602.94. That should seem reasonable because if they gave her $1,000 every year for 18 years, that's $18,000. But instead of having $18,000, she has $21,000. Why? Because she made over $3,000 in interest. Okay, for our next example, we've got Gary, who is 35 years old and saving for retirement. He's paid bi-weekly, and $100 from each paycheck is deposited into an RRSP. It's also compounded bi-weekly, paying interest at 3%. I mean, first of all, you need to know that bi-weekly is every other week. So Gary gets a paycheck every other week. There are about 52 weeks in a year. So he gets paid 26 times a year. Now, we'll come back to the RRSP part in just a minute. For now, all you need to know is the interest rate and the regular payments he's going to make. He's going to make these payments until he's 60. And we're going to figure out how much money he has to retire with. So $100 every other week for, in this case, 25 years. So the number of payments in this example will be 25 years times 26 paychecks in a year, which gives us 650 regular payments. Now the interest rate is 0.03, but it's compounded bi-weekly, so we'll divide by 26. Now there aren't exactly 52 weeks in a year, but we're not going to worry about that too much. This is still going to give us a pretty close to the right answer. So let's just look at calculating the future value here. The regular payments are $100. The interest rate, which we've shown to the side already, is 0.03 divided by 26 to the power of 650 minus 1 all over 0.03 over 26. If you plug all that into your calculator, I know it is tough and it does take some practice, you should get $96,727.36. Which is definitely not enough to retire off of. We'll talk a lot about that later on. The other question here is, how much interest has he earned? Well, if he made 650 payments of $100, then that is $65,000 that he put away. Yet he has $96,727.36. So the difference is the interest. So we get that just by subtracting. Which gives us interest of $31,727.36. So there's our interest that's earned right there. And this, of course, is our final or future value. Let's get back to this idea of the RRSP. What does that mean? Well, it stands for Registered Retirement Savings Plan, which is probably a term you've heard before. It isn't that much different than a regular savings account, like a GIC. In fact, it could be a GIC. It could really be any type of investment. The registered retirement part of it means it's specially designed for saving for retirement. And what happens is, as you probably know, once you're working full-time and you're an adult, you're going to pay income tax. And income tax is a lot of money. It's nothing compared to, sales tax is nothing compared to income tax. You might pay 30% on some of the money that you're making. Your income tax could be like 30% or so if you have a well-paying job. What the government does is they don't make you pay income tax on money you put into your RRSP. So maybe one year you put $8,000 into your RRSP. Well, that $8,000 worth of earnings might have been taxed at 30%, which would be $2,400 in tax. But since you put that money into an RRSP, you don't have to pay tax on that $8,000. And so you saved $2,400. So RRSPs save you a ton of money. Now, technically, when you're retired and you live off of that money, you do have to pay tax on it. But as we're going to see later on in this unit, that tax ends up being a lot less when you're retired. So RRSPs are very smart to purchase while you're working. And if you're still a little confused about the whole income tax thing, that's fine. We're going to go into that later on in the unit. Towards the end of the unit, we're going to look at some of those numbers together. Okay, let's move on to our next example. This next example, we have Carrie, and she wants to backpack around Europe in 3 years. And she's decided that she's going to need $5,000 to do that. And she's working maybe and decides that she'll contribute to a savings account every month. And the savings account pays interest at 1.75% compounded monthly. How much does she need to deposit in the savings account every month? Do you see how this is a much different question? We actually know what the future value is or what we want it to be. And instead, we're looking for what those regular payments need to be to get us to that amount. Let's just go back to the future value formula for a second. Oh, sorry, there it is right there. I want you to notice that we could actually rearrange this pretty easily. The first thing I'm going to do is I'm going to multiply both sides of the equation by I. So on the right side, the i's will cancel out. And I'll just be left with this right here. Then what I'm going to do is I've got that FV times I equals R times this mess here in the square brackets. So I divide both sides of the equation by that mess there, and I get R is equal to FV times I, all divided by that square bracket stuff. 1 plus I to the power of n minus 1. So this is like my rearranged version of this equation right here. So the future value equation can be used to solve for future values, or it can be solved for the payment amount, the regular payment amount that would be required to get a certain future value. And this is what we want right here in the example, with Carrie backpacking. So R equals FV times I over 1 plus I to the power of n minus 1. So in this case, we've got a future value of $5,000, an interest rate that's divided by 12 because it's compounded monthly. Okay, again down here as well. That's to the power of 3 years. So N is 3 times 12, 12 months in a year, which is 36. Just like that. So again, we need to type all of that into our calculator and see what we get. Let's do that together. I know it's a bit of a challenge, so I'll pull my calculator up again. And I'm going to start with the top of the fraction, 5,000 times 0.0175 divided by 12. And notice I didn't include these brackets here, but I could have. It's not, I don't actually need them. They're giving the same amount. So I just hit equals there to get the top of the fraction. Divided by bracket, bracket. Now, if you have a calculator that doesn't show the brackets when you punch them in, don't worry, they're still there, even if you can't see them. And if you can't see them, maybe you can find a calculator at home where you can. That would make things a little easier. Okay, 1 plus 0.0175 divided by 12, close the bracket, to the power of 36, take away 1, close that last bracket, hit equals, and there we go, $135, and round correctly to 38 cents. $135.38. One thing that I recommend, like you're wondering, is that question, is that answer correct? I'm having a hard time telling. So one thing you could do is you could do a good estimate. She made 36 payments of $135.38. Hopefully you understand that's 3 years, 12 months in a year, so 36 payments of $135.38, and she ends up with $5,000. Well, if you were to just take $135.38 and times it by 36, sorry, I'm going to do that again, $135.38 times 36, you get $4,873. So a little less than $5,000. That should make sense. The difference was the interest. So it only cost her $4,873 to get $5,000 because the money collected interest as she went. So if you're wondering, do people actually use this formula in real life? Well, I guess the answer would be, yeah, some people maybe do. I mean, I certainly would if I had a question about money that involved the final value of an annuity. But another option is to use an online tool called a TVM Solver. TVM stands for Time Value of Money. And a TVM Solver can be used to find the answer to all sorts of problems in finance, not just the ones that we're working on today. So if you were to just go to Google and type in TVM Solver, I will just go ahead and I will use the very first one I come across. And it's fine. And here it is. PV stands for present value. For now, make that 0. Payments is our R value here. Now they've called it PMT instead of R. Future value is FV. Interest rate here is an annual interest rate, so you don't have to divide by 12 or anything like that. Periods, that's our N value in this case, or kind of like time, the number of payments you make, and there's your compounding period. Also, make sure for your mode here, you have it at the end, because we're talking about annuities where the payments are made at the end of the month or the end of the year, or whatever it might be. So let's try this TVM solver and solve some problems. For example, suppose for 4 years, you put $20 a week into a savings account that pays 3.25% interest. What would the final value of this annuity be? So let's go to our TVM solver and see if we can figure out what to do. Leave the present value as 0. You can think about present value as being the starting value. The starting value is 0. You start with nothing, but you put in $20 a week. Payments, so we can make that into 20. Our interest rate in this example is 3.25, so I can just type it in as a percentage. And we're doing that every month. Okay, sorry, every week. So let's change this to weekly. Okay, now that's for 4 years. So one thing we do need to figure out is 4 years times 52 weeks in a year. We'll ignore the idea that, that might not quite work out that way. It's not exactly 52 weeks in a year, but that's fine. That gives us 208 payments, or 208 for our period here. So I type in 208. And then what I can do is when I click on this button, as long as everything else is filled in, it'll figure out the future value. And there it is there, 4,441.03. So that's the answer to the problem about the final value. Now we can also calculate the interest. So the interest will be equal to that 4,441.03 subtract 20 times 208. Now why am I doing 20 times 208? Because I'm basically saying, look, $20 for 208 weeks. That's how much I paid. That's how much I ended up with. So the difference was interest. In this case, it's only about $281.03. Let's go back to that TVM solver. I will show you something else about it. You may be wondering why this is a negative amount. Well, technically, if you want to use this correctly, our payments should actually be negative because our payments are what we're putting into it, okay? And then the future value becomes positive if we do it that way. You don't have to, though. It doesn't matter. As long as you just ignore the negative sign is fine, too. Let's look at another example. Mr. Elliott wants to have $1 million saved. He will make monthly payments for the next 20 years to achieve this goal. The money will collect interest at 2.82% compounded monthly. How much does he need to save each month? So how much am I going to put into that to make $1 million? So notice in this case, you have a future value. And you're looking for the regular payment. So we could certainly use the formula to solve this problem. Absolutely. But we could also use a TVM solver. And let's look at the TVM solver. Okay, so the interest was 2%. The present value is 0. The payments are unknown. The future value is $1 million. And how many periods are there? Well, this is for 20 years times 12 months in a year. They are monthly payments. So that would give me 12 times 20 is 240. So I'm going to make 240 payments. But my payments, my compounding is not weekly. It is now monthly. So I go up, I solve for my payments, and I get $3,392.17 each month. I don't think I'm going to be able to afford that. But that's what it would take for me to get $1 million in 20 years. You can use the TVM solver for lots of different things. I mean, you might look at this and say, okay, what about, suppose I can't afford $3,392. Maybe I can only afford, I don't know, $1,500 a month. And I need to get to $1 million. Well, then I could look and I could say, well, what interest rate? I could solve for the interest rate instead. Oh, I need an interest rate of almost 9% to do that. Probably not going to find an interest at 9%, but it is possible if you were invested in the stock market. That's not impossible, though it is difficult. I could also look and say, okay, the interest rate is 2% still, and I can only afford $1,500. I could solve for the period. How many months would it take me to get to $1 million? Oh, 448 months. Okay, so quite a bit more. So there's all sorts of things that you can use this TVM calculator to do. Now you might be wondering, why wouldn't I just use the TVM solver? Why would I ever use the formula? Or maybe you're thinking the opposite. Maybe you prefer the formula. I don't know. I think that you should be comfortable with the idea of using a formula like this, because that's probably one of the more important skills in mathematics, is to take a formula and be able to put values in it and evaluate it. I think that's very useful in many other areas besides personal finance. So I'd ask you to take the time to learn how to use the formula, but also take the time to play around with the TVM solver and realize that that's a great way to answer these kind of questions too. Okay, that's it for this lesson, and good luck with your worksheet. Bye for now.